Good morning. In the previous classes, we discussed about the size and shape of the Earth, and during that, we will mention about Earth has two types of motions: rotation about its own axis, and also Earth revolves around the Sun in an elliptical orbit. This is a common fact that we know nowadays. So now let's discuss some of the experimental proof for the Earth's rotation. The first one is the eastward deviation of a falling body. The another one is a experimental setup which is called the Foucault's pendulum, and also another thing is the gyroscope. The first experimental demonstration was done by Foucault, and using a pendulum which is almost similar to that of a simple pendulum, and which is called the Foucault's pendulum. So first experimental proof for the fact that Earth is rotating about its own axis is given by Foucault, and it is demonstrated by using Foucault's pendulum. Another thing is the gyroscope, which is actually a measuring device which is using which we can measure the angular velocity of Earth about its own axis. So we'll see each one of these three cases very briefly. The first one is the eastward deviation of a falling object. This is actually, by physics we can say that it is due to the Coriolis force, which is actually a pseudo force which appears to exist on an object when the frame of reference itself is rotating. We are not going into much details of these things, but just we will say how we can see the deviation of a freely falling object due to the Earth's rotation. Suppose this is Earth, and all of you know that Earth is rotating from west to east. Since Earth is rotating about its own axis, now if you consider the points which are near to the axis and which are far away from the axis, suppose there is a very high building here. Suppose this is I'm drawing like this. Suppose a building is here. This is on the surface of Earth and it is on the height. And here it will be the axis which is perpendicular to, suppose, this plane. Now when this Earth is rotating from west to east, then the building is also rotating, but the top of the building will be at a far distance from the axis, and the base of the building will be near to the axis of Earth. So in order to cover a large distance for the top to complete a rotation, the top of this building will be little bit faster when compared to the base of the building. Or we can say that the points which are near to the axis of rotation will move slowly compared to the points which are away from the axis of rotation. Or we can say that if the Earth is rotating about an axis, then the points which are at a greater distance from the axis must move with greater velocity than those which are near to the axis. So we can say that the top of a high tower has a slightly greater velocity than the base Then if you consider a stone is dropped from the top of this tower, the stone is initially having a greater speed because it is at the top of the tower. When it is dropped, then you can see that if it was not dropped, it should have moved a large distance. Suppose this is the distance moved by the stone because it is having a greater speed at the top of the tower. Suppose if it was at the bottom, it should have been moved a smaller distance, since the velocity of the objects or the speed of the objects near the axis of the earth will be small. But when the stone is dropped from the height or from the top of the tower, it should have a greater speed compared to the base, or we can say that compared to the object in the base of the tower towards the eastern side, because earth is rotating from west to east, so it would have been reached somewhere here. If it were in the top, it is not dropped, it should have reached at this point, because the top of the tower should be reached here at a further distance. But the base should be like this. Suppose this is the tower, it would have been moved like this. But the stone will reach some point here. Now we can say that somebody standing here will observe that or somebody standing here will observe that the stone has a little eastward deviation when it is allowed to freely fall from a top of the tower. This is due to this rotation of earth about its own axis. So that is one of the experimental evidence for the rotation of earth about its own axis, that is every freely falling body will have a eastward deviation due to the earth's rotation, and the force responsible for this eastward deviation is the Coriolis force. So this is one of the evidence. Now another one is the Foucault's pendulum. This actually in 1851 Foucault in Paris demonstrated an experiment that it almost using a simple pendulum, which actually consisting of a long string which is almost 72 meters in length, and the bob has a mass of 28 kilograms. This is used in order to avoid the local perturbations which affect the motion of this pendulum. When this pendulum is allowed to swing, you know that every simple pendulum will have a movement like this. It is oscillating in between these maximum amplitudes, and here we will have a plane of oscillation. When a Foucault pendulum is set up in any point on the surface of earth except at the equator, you can see that the plane of oscillation of pendulum will rotate from east to west. Since earth is rotating from west to east, any observer who is observing a Foucault pendulum on the surface of the earth except at the equator will observe the plane of oscillation of this pendulum will also rotate with an angular velocity, actually omega sin phi, where phi is the latitude at that place, and the direction is from east to west. And the third one is the gyroscope, which is actually an experimental setup. It is not only to demonstrate the Earth's rotation, but also it is used to calculate the angular velocity of Earth's rotation, and it is a spinning wheel or a disc in which the axis of rotation is free to assume any orientation by itself. So if Earth were not rotating or it is stationary, the axis of this gyroscope will be also stationary, or it is not having any change, but depending on the angular velocity of the Earth's rotation, the axis of this gyroscope will also rotate. So in simple or in brief, I can say that these are the different experimental proofs for demonstrating the Earth's rotation. One is the eastward deviation of a falling object, the second one is the Foucault's pendulum, and third one is the gyroscope. Now you know that in addition to this rotation of Earth will have a revolution around the Sun, which is a very common fact to us nowadays, but it is in beginning of the 16th century it is actually demonstrated by or made in the form of a law by Kepler, and which is treated to be the beginning of the modern astronomy, which is called Kepler's laws of planetary motion. Johannes Kepler, at the beginning of the 17th century, enunciated 3 laws regarding the orbits and motion of the planets. First one is the law of orbit. These things are very familiar to you, those who have done the science group in +2. Anyway, just we will briefly discuss about these 3 laws. That is, these 3 are the laws, first laws put forward by Kepler to introduce the planetary motion around the Sun, and which is treated to be the beginning of the modern astronomy. The first law is the law of orbit. That is, it says that every planet moves in an elliptical orbit with the Sun at one of the foci. That is, if you consider the Earth and the Sun system, then suppose this is the Earth, then Earth is a planet which revolves around the Sun in an elliptical orbit with the Sun at one of the foci. That means if an ellipse will have 2 focus, F1 and F2, then Sun will be at one of the foci. So suppose Sun is here, then the Earth will rotate around the Sun in an elliptical orbit around the Sun. So that is the first law regarding the orbital motion, and which actually gives the shape of the orbit. The first law gives us the shape of the orbit. Now the second law is called the law of area. That actually the straight line drawn from the Sun to the center of the planet, which is called the planet's radius vector, sweeps out equal areas in equal intervals of time. That means if you consider a time period t and suppose earth is at this point and after this line is called radius vector, that is the vector drawn from the sun to the center of the planet, which is called the planet's radius vector. And when the planet moves and reaches this position, let's say this is the position 1 and it is the position 2, then as the planet moves from the position P1 to P2, let's say it takes a time t and the radius vector sweeps out this area in t time. Now suppose at a later time the planet is at this position, let's say P1 prime, and after a time t it reaches the position P2 prime, then this line actually represents the radius vector SP1 and this one represents SP2, and this is the area traced out by this shaded region is the area set out by the planet at the time interval t. So now here this one, the area P1S P2 is the area set out by the radius vector during a time t when the planet is at this position, and this is the area set out by the planet, that is SP2 prime. P1 prime is the area set out by the planet at the same time t. Then these two areas are equal. That is the second law of Kepler's planetary motion. So that is otherwise called a law of area. So in simple words we can say that the area swept out by the radius vector is same in equal intervals of time. Otherwise we can say that if this is delta S1, the area is delta S1, this is delta S2, the area, and the time is t, let's say delta t, and this is also delta t, then delta S1 by delta t will be equal to delta S2 by delta t, or delta S1 equal to delta S2. So this delta S1 delta t is called the rate of change of area with respect to time, which is called the aerial velocity. So aerial velocity of a planet is constant. That is the another statement for the Kepler's second law of orbit. Now the third one is the law of periods. It says that the square of the time period of the planet is directly proportional to the cube of the semi-major axis. Since I told you an ellipse will have two focus, similarly the ellipse will have two axes. One is called the semi-major axis A, and this is called the semi-minor axis, and this is represented by B. So according to Kepler's law of planetary motion, the square of the period of the planetary motion is proportional to the cube of the semi-major axis, that is t square proportional to a cube. That is the third law. So these are the three statements made by Kepler based on different observations, and they put in the form of laws, and they are called Kepler's laws of planetary motion. One is the law of orbit, which actually gives the shape of the orbit, and it states that every planet moves in an elliptical orbit with the sun at one of the foci. The second law, which actually called the law of area, which gives the which says that the aerial velocity is a constant, so it actually represents the speed of the planet around the orbit at different positions, and it is states that the statement is like this: the straight line drawn from the sun to the center of the planet or the planet's radius vector shifts out equal areas in equal intervals of time. And the third one is regarding the period and the distance of the planet from the sun, and which is called the law of periods, and which gives states that the square of the time period of a planet is directly proportional to the cube of the semi-major axis. Now, one more thing which we have to deduce from this second law is that I told you the aerial velocity is a constant. That means if you consider sun is at this point, the planet at this position is P1, and the planet after a time, let's say delta t, moves to the position P2. Then SP1 is the radius vector when the planet is at the position P1, and SP2 is the radius vector when the planet is at the position P2. Then this shaded region is the area swept out by the radius vector of the planet at time interval delta t, and after a long time, suppose the planet reaches another position, let's call it as P1 prime, and after a time interval delta t, the same time interval delta t, the planet reaches the position P2 prime. Then SP1 prime represents the radius vector when the planet is at the position P1 prime, and SP2 prime represents the position of the planet at or radius vector of the planet when the planet is at the position P2 prime. Now this shaded region or shaded area represents the area swept out by the radius vector at the time interval delta t. Now if you consider these areas according to the second law of planetary motion, these two areas are equal. That means if you consider delta S as the area, then delta S is a constant, or we can say that delta S by delta T is equal to a constant. But delta S, actually the area, if you consider this distance is delta R and this is R, then this shaded area will be delta S is equal to, it is almost like a triangle, so its area is half into R cross delta R. It's a vector. So delta S by delta T will be 1 by 2 into R cross delta R divided by delta T. So it is change in position by changing time. It is nothing but the velocity v. So this equation become 1 by 2 into R cross v. When at the limit delta t tending to 0, which is called ds by dt, the aerial velocity. So ds by dt, we obtained it as 1 by 2 into R cross v. Which is equal to, when we consider the velocity in terms of the angular velocity, R can be written as R cross omega or omega cross R, depends on the direction. Then if you substitute it here and do the vector triple product, you will get half R square omega. So half r square omega is a constant according to the Kepler's laws of planetary motion, or specifically according to the second law. So this half r square omega, or you can write omega is equal to some constant divided by r square into 2. 2 is also merged into this constant, so that constant we are denoting it by h, then it is h by r square. Or you can write omega is proportional to 1 by r square. That means the angular velocity of the revolution of a planet around the sun is inversely proportional to the distance square of the distance of the planet. So this actually gives the speed of the planet around the sun. So that's why the second law gives the speed of the planet. So that is another thing which we can draw from the second law of Kepler's second law of planetary motion. Now we have to discuss some of the consequences of the Kepler's second law that we will discuss in the next video. Thank you.